Hello everyone, myself Renuka Mannam. My advisor is Dr. Prashant Kumar Ghosh. We are from Spire Lab, ISC Bangalore, India. In this video, I am going to present our accepted paper titled as Speech Data Specific Representation Learning from Acoustic Articulatory Data. These are the contents that I am going to discuss. First, I start with the introduction and I discuss about the data set used in this work, then proposed approach and experimental setup. Then I discuss the results and conclude. The goal of the paper is automatic estimation of the speech rate using acoustic articulatory data. The acoustic and articulated representations are learned in a task-specific manner. Speech rate is a paralinguistic information which is encoded in speech over a long duration. Speech rate is calculated as the number of syllables per second in a given speech segment. In this work, we consider vowels as syllables similar to the prior works in the speech rate estimation. Speech rate is altered by emotional state, nativity, and health condition of a speaker, which affect the performance of the many speech related to such as speech recognition, emotion recognition, and speaker identification. Before going into the details of the proposed approach, let's first understand the need of articulatory data. As we know that human speech production involves modification of the vocal tract using various articulatory configurations. Different sounds have distinct articulatory configurations. Articulated representation contain information complementary to acoustics. It is observed that a speech task could benefit from both acoustic and articulatory data. However, data is not directly available. Unlike speech recording, thus we use an acoustic to articulate inversion model (AI) model to estimate the articulated representations from acoustics. To understand the need of task-specific representation, we need to know the disadvantage of generic representations and their definition. These generic representations are extracted in a knowledge-driven manner and they may not be optimal for all the speech tasks. Examples, MFCCs and subband energies. The representation estimated from AI are pseudo and generic in nature and they may also not be optimal for all the speech tasks. Thus, the acoustic and articulated representations need to be learned in a task-specific manner. In this work, we learn task-specific representations from task speech waveform using one-dimensional convolution filters, and task-specific pseudo-articulated representations are learned by jointly training the AI and the model for speech rate estimation using a weighted loss function. In this work, we use two types of corpora. One is timid corpus and the other one is IEEE corpus. The timid corpus consists of 630 subjects from 8 major dialects. There are total 5040 sentences. The timid corpus is used to evaluate the proposed approach for speech rate estimation. The ground truth speech rate is calculated as the number of vowels divided by the total duration of the speech chunk. The speech rate for the 1 second duration chunks varies from 2 to 8 vowels per second. As the timid corpus does not consist of articulated data, we use IEEE corpus to train and evaluate the AI model and to generate articulated representations for timid corpus. The corpus consists of simultaneously recorded audio and electromagnetic articulography data for 720 sentences from 8 speakers, 4 male and 4 female, and multiple speaking rates. The sampling frequency of audio is 44.1 kHz. The MR recordings are obtained using 8 sensors placed on tongue, dorsum, tongue base, tongue tip, upper lip, lower lip, mouth, ear, jaw and jaw left in X and Y jet coordinates. The sampling frequency is 100 Hz. In this work, we consider X and Y jet coordinates for the 6 articulators except ML, JL as articulated representations. Before discussing the block diagram of the proposed approach, let's first understand the flow of the approach. As shown in the figure, we utilize both acoustic and articulated representation for the speech rate estimation. As the acoustic data is not directly available, the articulated representation are estimated from acoustics using AI. As the representation from AI is generic in nature, we run the task-specific representation by jointly training the AI and speech rate estimator. We also learn the task-specific acoustic representations which are optimal for the speech rate estimation. Figure illustrates the block diagram of the proposed approach using task-specific representation learning. As shown in the figure, we use concatenated acoustic and articulated representations as input to the CDNNT model convolution dense neural network to estimate the speech rate. We explain each block in detail in further slides. Figure illustrates the architecture of the CDNN, which consists of convolutional, max pooling, and dense layers. We formulate speech rate estimation as a regression problem, hence we use mean square error loss to optimize the weights, which is denoted as LSR. In this work for AI model, we use bidirectional long short-term memory network with 256 nodes. If the input MFCs has a dimension of t cross 39, where t is the number of time frames, and output MO points have a dimension of t cross 24. The output MO points consist of x and z coordinates of 6 MO points tt, tb, tt, ul, ll, and ja, and their magnitude of velocity and acceleration components. The articulatory points estimation problem is stated as a regression problem, hence mean square error loss is used to optimize the weights, which is denoted as LMO. As explained earlier, the speech rate specific pseudo-articulated representations are estimated by jointly training the AI and CDNN models using a weighted loss function, which is denoted as shown in equation 1, where LSR is the loss corresponding to speech rate estimation and LMI is the loss corresponding to the MO points estimation, and W is the weight which ranges from 0.1 to 0.9 with a difference of 0.1. For each W value, the AIJ, CDN, and IJ model is trained using the IEEE MR corpus, where J stands for joint and I stands for IEEE MR corpus. To generate the articulated representations for timid corpus, we use AIJ model, which provides the best performance for speech rate estimation, and IEEE MR test data using AIJ, CDN, and IJ model. The AIJ model provides the speech rate specific pseudo-articulated representations. As explained earlier, we use 1D CNN to estimate the speech rate. Specific acoustic representations. We perform some pre-processing steps. The speech signal is downsampled to 8 kHz and windowing is done using a Hamming window of length 35 milliseconds and a shift of 10 milliseconds. The speech rate specific acoustic representations are learned from the speech frames as shown in this equation 2, where Sn is the nth speech frame with a dimension of WL, which is window length. The output has a dimension of WL minus FL plus 1 cross FL, where FL is the filter length and FN is the number of filters. K is the set of FN one dimension convolution filters and B is the bias vector. The logarithmic operation is performed to mimic human listening. On the output, we apply a max pooling of size WL minus FL plus 1 to discard the short-term phase information. Thus, the final output is the dimension of Fn, which is the number of filters. In this work, we consider FL equals to 240 samples and Fn equals to 32. As the final model, we use Con1D, CDN, and CJT, which uses the concatenated task-specific acoustic and articulated representations, where T represents timid corpus, J represents joint, and C represents concatenation. The Con1D and CDN models are jointly trained. The Con1D output and AIJ model outputs are concatenated and fed to CDNN. The Con1D and AIJ models provide speech rate specific, acoustic, and pseudo-articulated representations respectively. This completes the explanation of our proposed approach. We use temporal correlation and selected subband correlation, TCS's BC feature contour based approach, which involves peak detection with smoothing and thresholding operations. The TCS's BC approach is an unsupervised approach. We also use other CDNN based approaches, which is CDNNT, which uses MFCCs as input, and Con1D CDNNT, which uses speech rate specific acoustic representations as input. AI CDNNT uses generic articulated representations as input. In this AI model, AI is independently trained without using speech rate estimation. The AI model is used to generate the pseudo-articulated representations for timid data, which is used as input to CDNN. In the AIJ, CDN, and T model, the task-specific pseudo-articulated representations are used as input to the CDNN model and speech rate as output. The experiments are done in seen and unseen subject condition in a 4-pole cross validation setup using timid corpus. As an evaluation metric, we use Pearson correlation between the estimated and ground to speech rates. Figure illustrates the 4-pole cross validation setup in seen subject condition. In this, the test set contains the sentences from the subjects which are involved in training. For all the 630 subjects, we divide 8 sentences from each subject into 4 sets, so that each set consists of 2 sentences per subject. Among the 4 sets, 2 sets are considered for training, 1 set for validation, and 1 set for testing. Figure illustrates the 4-pole cross validation setup in an unseen subject condition, in which the test set contains the sentences from the subjects which are not involved in training. The 630 subjects are divided into 157 subjects, 4 sets, such that each set contains 157 subjects per set. Among the 4 sets, we consider 2 sets for training, 1 set for validation, and 1 set for testing. Table illustrates the CC values for MO points estimation and speech rate estimation using the joint and AIJ on IEEE AIJ, CDN, and IJ. on IEEE test data for W values ranging from zero point 0.1 to zero point 0.9. As the W value increases, the CCMR value is increasing because the penalty for the ROS corresponding to MR points is more than the penalty for the speech rate estimation. Hence, the model concentrates more on the accurate MR points rather than on the speech rate estimation. However, as the W is increasing, we did not observe a consistent drop in CCSR value. The best CCSR value is obtained from W equals to zero point 0.7, and the independently trained AI model AI and jointly trained model AIJ provide 0.7310 and 0.6893 CCMR values respectively. The drop in the CC value corresponding to AIJ is observed because the training involves not only the MR points estimation but also speech rate estimation. Table provides the average and standard deviation of the CCSR value for all the baselines and proposed approach in seen and unseen subject condition on timid test data across the four folds. Different input representations are also mentioned in the table. It is observed that using both acoustic and articulated representation help in better speech rate estimation, and the proposed approach performs better than the all the baseline approaches, and speech rate specific pseudo articulated representations provide better performance compared to the generic pseudo articulated representations. And compared to MFCCs, star specific representation provide better performance in seen subject condition and comparable performance in unseen subject condition. Figure illustrates the log magnitude response of the 3211 con 1D filters in con 1D CDNNT, which does not use articulated representations, and con 1D CDNN CJT, which uses pseudo articulated representation. The x-axis indicates the frequency in hedges, and y-axis indicates the sorted filter index, and the color intensity indicates the magnitude. It is observed that both the magnitude response have high magnitude values in low frequency regions compared to the high frequency regions. Thus, the length filters emphasize syllable nuclear regions which lie in the low frequency regions. However, in the case of CON 1D CDN and CJT, the magnitude of side lobes is attenuated in high frequency regions compared to this. Thus, the articulated representation help in learning better task specific acoustic representations. Figure illustrates the center frequencies of the learned con 1D filters from con 1D CDN and CJT, which uses articulated representations along with acoustics, and con 1D CDNNT, which does not use articulated representations, and MFCC's filter banks. It is observed that the con 1D CDN and CJT has more number of filters with center frequencies below 1000 Hz. Figure illustrates the spectral trajectories of the jaw tongue tip in Z direction from IEEE ground truth estimated using AI and AIJI for a sentence from IEEE data, and estimated using AI and AIJ for a sentence from timid data. The vertical red lines indicate center frequency corresponding to the 99% of the energy from the entire trajectory. It is observed that the original pseudo and task specific pseudo-articulated representations are following low-pass filter characteristics, capturing the smoothly varying characteristics of the articulatory point. To conclude, task-specific representation perform better than the generic representations. The concatenated task-specific acoustic and pseudo-articulated representation help in accurate speech rate estimation. The proposed approach performs better than the speech rate estimation compared to the baselines. Our future work includes predicting syllable nuclei jointly with the speech rate estimation. Others thank the Pratiksha Trust and Department of Science and Technology, Government of India for the support. Thank you. If you have any questions or suggestions, please write to us at spirelab.ee@iasc.ac.in.